One of my students asked the other day why the geometric series test and the p-series test looks completely different from each other. Because for example, we know that the geometric series can converge when r less than 1. The p-series can converge when p greater than 1. So exactly opposite to each other. So the whole purpose of this short video is to explain what is the reason behind. So let's start with the basics. We need to know what is a geometric series means. So geometric series means that's going to relate to the geometric sequence. So what's a geometric sequence? You're going to start with the constant, and then we're going to multiply by a fixed number every time. So we're going to call that fixed number r, or the ratio. So we're going to multiply by r. So that means the second term going to be ar, third term going to be ar squared, fourth term going to be ar cube, like that. So that means you can see the general term looks like ar, not n, because you can see the fourth term is 3, so ar n minus 1. So that's how the general term look like. Now what we can do, we can add them. Once you add them, we get what we call the geometric series. So this is geometric sequence. So this is the sequence, and then when you add the corresponding terms, we get the series. So let's try the geometric series. So that means the sigma. We can start with n. So let's say n going from 1 to infinity. We can add, and then we write the general term. So which is a r n minus 1. That's how we write it. And then you can see that this is simply when you plug n equal 1, you can get AR0, that means A, and when you plug in n equal 2, you get AR, like that. So that is the series as a representation. Now the question is, when this can converge? And we discussed that we know that this series can converge when so let's try the condition. So we know that if the absolute value are less than 1, we know that the series can converge, geometric series converge. If the absolute value are greater than or equal 1, so exactly the opposite, then we know that the series can diverge. So you can also remember that the absolute value are less than 1, um, then if and only if the series converge. So it's if and only if. That means if one of them is opposite, then the other one is also opposite. So that is the geometric series condition. So that means if you look at this on a number line, you can see that. So let's say this is a number line. So let's put this information. So we have 1. So 1 is the important number here. And then what's going to happen? So anything bigger than that, anything actually, so you can see absolute are less than 1. So less than 1 means, so there are two numbers. So absolute less than 1 means you can see that the r is in between, two values. That means 1 and negative 1. That's what absolute r less than 1. So the size is less than 1 of so that means the value is in between those two numbers. So so this is 1 and the negative 1. So this is negative 1 and 1. So you can see that the series can converge only in this region. That's where the series can converge. So series can converge here. So outside, because this is when r absolute r greater than or equal 1. So this is the absolute value r less than or equal negative 1. So on those two sides, what's going to happen? Series can diverge. So those two sides series diverge. So diverge and diverge. So that's about the geometric series. Now let's look at the p series. So p series. So what's p series? So we normally write p series. We go in going from 1 to infinity. So it's 1 over. That makes the whole difference there. So 1 over n to the p. That's what we call the p series. And we know about the p series. So for the p series, when p greater than 1, the series is going to converge. And then when p less than or equal to 1, the series is going to diverge. So you can see that if you look at the condition, this condition, so here the absolute r less than 1 is going to converge, the geometry series converge. And for the p series, when p greater than 1, the series is going to converge. And then you can see that, so if you change absolute value r to p, is exactly opposite of that. So absolute value r and p um, act exactly opposite. The main reason for that is you can see when you write the geometric series, your r is on the numerator. But when you write the p series, you can see the np is in the denominator. So that's going to change from top to bottom. So that since it is changing from top to bottom, inequality change the other way around. So that's exactly what happened because where you write the term. So in the geometric series, you write the term on the top, it's arn. And when you write the p series, you can see that you're going to write the term in the denominator. So that's going to change the inequality the other way. So that is the main reason why the geometric series has less than and why the p series has a greater than sign. So again, let's draw the number line here. So if you draw the number line, so you can see that the um, so if you look at the convergence part, so you can see it's going to converge 1 up. So that's 1 and up. So that's where it's going to converge. Um, so that's the only important one. So that's why we write only that one. So that's 1. So 1 up is going to converge, and everywhere else is going to diverge. So if you look at the rest, so this where it's going to diverge. So if anything below 1, so this is p greater than 1. So this is where p less than or equal to 1. So that's you can see that's the main difference in the two tests. So um, so geometry series converge when absolute are less than 1. The p series converge when p greater than 1. The main reason is in the geometric series you write r in the numerator. In the p series we write np term in the denominator. So that's the major difference. So let's look at a few cases to see how it works. So let's look at some example from geometric series. So geometric series. So as the first one, let's start with the simple series. So 1, you start with 1 and you every time you multiply by x and then x squared like that. And we know that this series we can write it like this, n going from 0 to infinity, x to the n. And we know that this series can converge to, this series can converge to 1 over 1 minus x when the absolute value of x less than 1. So that's you can see because the reason here is you can see that r is simply equal to x. So because you multiply by r item here, r is equal to x. So that means absolute r less than 1. So that means absolute x less than 1. So that's what you get. And then, so let's look at another one. And for the geometric series, we also have a formula. So what's the formula? So we know that for the absolute value r less than 1, we can write sigma n going from 0 to infinity a r n minus 1, which is a plus a r plus a r squared like that. So this is simply a over 1 minus r. So that's where it's going to converge to. And if it is outside, then it's going to diverge. So we can write anything like that. Good. So let's see how we can use this fact. So for example, let's look at this one. So let's say sigma n going from 1 to infinity. Let's say 7. negative 0.03 to the n, or something like that. So and then you can see that in this case R, so this is R. You can see the pattern, so that's R. So you can see that R equal negative 0.03. So that means this implies that the absolute value R is 0.03, so it has to converge. So the series converge. So this implies series converge. Um, and also we can do another one like this. Let's say we have sigma, and also we don't need to start with always 1, so you can say like that. So it is e to the pi to the, let's say, n minus 1, something like that. And then you can see in this problem also R equal e to the pi. So if you look at these values, these are roughly e means 3 point e means 2.7, e means 2.7, and pi means 3.1. So that means if you divide, you get 1. So this implies that converge. Now the question is converge to what? So we can use a formula. So in going from 4 to infinity, e over pi to the n minus 1. This is a over 1 minus r. So a means the first term. What's the first term? You need to find the first index. First index is 4. So if you plug in 4, you're going to get e over pi to the third power divided by 1 minus e over pi. Now the question is how to simplify this. To simplify this, what we can do is we can multiply the top and bottom by pi to the cube. So if you do that, you can see that it's going to be e cube divided by, when you multiply pi to the cube, if you multiply by 1 of pi, it's going to simplify the fraction in the denominator, and you left with e squared. So it is pi minus e. That's what you get, and that's where it's going to converge to. So let's look at another problem like as a regular geometric series problem. So like how about this one? And going from let's use something else. Let's say k. So k going from 2 to infinity. Let's say we have 3k minus 1 over 2 to the 2k plus 3, something like that. So what you only worry about is the terms that has a k. So those are the terms that you can isolate. So that means if you get a problem like that, what we do is sigma k growing from 2 to infinity. So it is 3 to the negative 1 and then 2 to the 3. And you can see that it's a 3 to the k coming from the top, 2 to the 2k coming from the bottom. And you can also see that you can simplify this a little bit more. So this is simply sigma k going from 2 to infinity. If you bring 3 down, 2 to the 3 means 8, so it's going to be 2 times 8, 24. And then you can here 3, 2 means 4, so it's going to be 4k. So you can write it like that. So the reason is we know that 2 to the 2k you can write as 2 to the 2 to the k, like that. That's the reason. Good. Now you can see this is a geometric series, and then we can see that R is 3/4, which is less than 1. So converge. So you can converge. So and then we also know what's the sum, so we can plug into the formula. So in this case, A means the first term. So what is the first term? You need to plug in the first index value, and you can see the first index value is k equal 2. So if you plug in k equal 2, you get 3 to the 1, which is 3. And then from the bottom, if you plug in k equal 2, you get 2 to the 7. and then 1 minus, it is 3/4, that's r. Now again, how to simplify? You can multiply the top and bottom by 2 to the 7. So if you multiply by 2 to the 7, and you can see that you end up getting a 3 in the numerator, and in the bottom you're going to multiply by 2 squared, then you get 4 minus 3, which is 1, and then you left with 2 to the 5th. So yeah, it's a 2 to the 5th, 4 minus 3. So and you can see that this is 3 over 32. Good. That's what you get for these kind of problems. And let's do just one more. Uh, like what if you have a negative sign like this? So you can see sigma n going from 0 to infinity, negative 1 to the n, 2 to the n, let's say e to the n, e to the n, like that. So if you get something like that, you again can isolate all the terms with n. So in this case, everyone has an n, so that means you can write this one as negative 2 over e whole thing n, like that. Now you can see what is r. So r is negative 2 over e. So if you look at the absolute value of r, which is 2 over e, since e is more than 2, so this is less than 1. So that means series gonna converge. And we know the sum. So sum is a over 1 minus r. In this case, a is 1. Because when you apply n equals series 1 over 1 minus minus become plus, so 2 over e. Now what we're going to do, we're going to multiply the top and bottom by e. So if you do that, you get e over e plus 2. So that's where it's going to converge. So that's about that. So let's look at a few some of the interesting examples from actually before the let's do one last one. So how about this one, sigma n going from 0 to infinity, negative 1 n, negative 1 n. And if you look at this one, you can see in this case r is equal to negative 1. So if you look at the absolute value r, which is 1, so that means this is less than or equal to 1. Actually greater than or equal to 1, not less than. So this is the geometric series. So it is greater than or equal to 1, so diverge. That means the series is going to diverge. Good. So that's about that. So let's look at some example from pSeries. So example from pSeries. So let's say something like this: sigma n going from 1 to infinity, 1 over n. So in this case, you can see that in this case p equal 1. So that means it's going to diverge. Diverges since p equal 1, which is less than or equal to 1. When you do the p series, if it is less than, it can diverge. Less than or equal to 1, it can diverge. And also this has a special name. This is what we normally call the harmonic series. When p equal 1, this is the harmonic series. So let's look at a few more examples. How about this? So we have this special series, what we call the theta s. So this is sigma n going from 1 to infinity, 1 over n to the s. So this has a special name. This is what we call Riemann theta function. So Riemann theta function, called the Riemann theta function. This has very nice applications. So and then you can see that this is just a p series. So you can see that this can converges for any s greater than 1. So if you have s which is greater than 1, it's gonna converge. Okay, because it's just a p series. now the question is, when you have P series, do we really know the sum? So there are just few ones that we actually know the exact value. So let's look at some of those special cases of those Riemann um, series. So let's say this one. Uh, so sigma n going from 1 to infinity 1 over n squared. This is you can see 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, like that. But this series has proved is converged because p equal 2, so that means which is more than 1, so it's going to converge. And Leonhard Euler proved that this can converge to pi squared over 6. So this was proved by Leonhard Euler. Pi squared over 6. It's like nice proof. So there are only few that you can show that's going to converge and get the exact. Actually, you can show it's going to converge, but the exact value would be a little different. So in this case, we know that's a p equal 2, so it has to converge. And also we know formulas for few other cases. So like for example, if we have n equal 4, we know that. So n equal 4, that means 1 over n to the 4th power. So this is 1 over 1 squared, 1 over 2 squared, not squared, a 4th power. So we have 1 or 1 to the 4, 2 to the 4, and 1 over 3 to the 4. And also you can show that this can converge to pi to the 4 over 90. So that's again Euler proved that. So and then also when we have next even number, that means 6, 1 over n to the 6, you can also prove that it's gonna have 1 to the 6, 1 over 2 to the 6, 1 over 3 to the 6, like that. And then you can show that you're gonna end up getting pi 6. That's interesting. And then 9 45. So those are the kind of few ones that we know. So this for even powers. But interesting thing is, if it is an odd number and there is no uh, exact answer for that, so you only have approximations. So for example, if you write n going from 1 to infinity, 1 over n to the cube, so you can see it's not much difference. So I mean, not big difference, but it just 3 is odd number, and you don't have exact answer for that, you only have approximation. So you can see that this can approximate to 1.2020569, like that. So the same thing if you for example put n equal let's say 5. So if you put n equal 5, and you can show that it's also going to not exact formula, so it's gonna get like something like 1.0369278, something like that. Okay, so that's the case. So for even we have exact formulas, but for odd numbers we do not have exact formulas. So those are the kind of interesting example. So let's look at maybe just 3 more interesting ones. So how about sigma n going from 1 to infinity, 1 over n to the pi over e. So in this case you can see that the p equal pi over e. So pi is 3.14, e is 2.71. So this is roughly 3.14 and 2.71. That means this is bigger than that. So that's since it is larger, this one has to converge. Okay, it's going to converge. Since p are greater than 1. And then how about this? Let's say you are going to take the square root of this. 1 over n pi over e square root. So you can see that they still converge, since if you take a square root of a number which is more than 1, that's still more than 1. So that's something coming from basic algebra. Um, okay, so and then what's gonna happen? So let's say, because these are like all the p series, but there are some series which are very close but not exactly p series. For example, alternating series. Alternating series. So for example, if you look at this one, sigma n going from 1 to infinity, -1 n over -1 n 1 over square root n, something like that. And you can see that this is an alternating series, and also you can see that this term, if you look at this term, this is gonna go to 0 and also decreasing, so that means this gonna converges due to the alternating series test. But this is not exactly a p series, but it's very close to p series, because the sign chain, and it's not a geometric series, so it's very close to p series. But if you use alternating series test, you can easily show that this can converge. So this is a kind of related material about the geometric series and the p series.